This lecture is a continuation of the thermodynamics of phase change lecture. In this part, we're going to look at how to do the calculations associated with phase change and with increasing and decreasing the temperature of a substance. In the previous lecture, we talked about two different types of characteristics for a substance that helps determine, or which is used to determine how much energy is going to be required to either warm the substance or to cause it to melt or undergo a phase change. And these were specific heat and molar heat. So let's look at these definitions one more time. The specific heat capacity, abbreviated as CP, is the amount of energy that's required to increase the temperature of 1 gram of a substance by 1 degree Celsius. If you wanted to decrease the temperature, that's the amount of energy that would be released. The molar heat of fusion, abbreviated as HF, is the amount of energy that's required to melt 1 mole of a substance. If you're looking at a different phase change where you are boiling, you're going to use a different value, which is the molar heat of vaporization, HV. Vaporization basically means boiling. So you can think of the word evaporation, which is similar, and they both have a V, so that might help you remember that vaporization is the one with a V, like evaporation. And fusion is the opposite process of melting. So fusion is like freezing, which both start with an F. So let's look at where you would use these. If you're solving a problem in which you are taking a substance and you are heating or cooling it, then the part of the problem in which you're looking at the change in temperature is going to use this equation here. In this equation, you have energy, which is going to be measured in joules or calories, the mass of the substance in grams, the change in temperature, and you're going to use the absolute value and the specific heat capacity value. You'll find that on a table or a reference table. You can find that, and you would plug that number in. If you are increasing the temperature, then Q is going to be a positive number. If you were decreasing the number, then technically this would be a negative number, so you would have a negative Q. Negative Q just means that energy is being released. To simplify this for our calculations, we're just going to use the absolute value of the temperature, and then we're just going to have the absolute value of energy involved. If you have a calculation that is involving a phase change, however, you will need to use this equation, in which we're going to use the molar heat. If that phase change is going to involve a substance that is melting or freezing, which are both, they're essentially the same process, using the same degree of energy. One is just positive and one is just negative. Either way, you're going to use HF. If, however, you're doing a phase change that involves either vaporization, which is boiling, or condensation, which are the same process, just one is positive and one is a negative value in terms of the phase change or entropy, then you are going to use HV. And again, HV and HF are characteristics of a substance that you would look up on a reference table. And again, you're going to use M is for the mass in grams, and energy is either in joules or calories. In a previous lecture, we looked at this phase change curve. This one happens to be for water. The reason we know it's water is because we know water is going to melt or freeze at 0 Celsius. And either boil or condense at 100 degrees Celsius, depending on whether energy is being removed or added. But what we want to look at is, depending on what part of the phase change curve you are looking at for whatever problem you're solving, you're going to use a different equation. So at any point where the temperature is increasing, notice that they all use the same calculation, and that is the calculation involving CP, or heat capacity. So you would use different heat capacities. Most substances will have a heat capacity for solids, a heat capacity which is slightly different for the liquid phase, and one that is slightly different for the gas phase. One way to remember that this is the appropriate equation to use is that you can see in this part of the phase change that temperature is changing. And in this equation, there's a space for you to put a change in temperature. If your calculation involves a phase change, however, which would be boiling or freezing is right here, melting or freezing is there, boiling and vaporization or condensation is here, you are going to use the other equation, which involves molar heat. Again, the molar heat of fusion, you can think of this F as in the molar heat of freezing. We would use the same equation and the same value for that substance, regardless of whether you are freezing or melting. If you are melting, then you are adding energy, and your energy is going to have a positive value. If you are removing energy in order to freeze a substance, making the energy go down, you would have a negative value. This is the same for if you are boiling or condensing. When you boil a substance, you're going to be having a positive inflow of energy. If you are condensing the substance, you're going to use the same value of HF. However, you know that you are removing energy, so your energy will have a negative value. Again, to simplify this, we're always just going to use our Q. We're going to make our energies a positive value, and we're just going to refer to them as being either absorbed or released. So just to emphasize that specific heat capacity refers to the energy involved in energy being released or absorbed. We can also sort of change these definitions around to say that specific heat is the amount of energy released when the temperature decreases. And likewise, molar heat of fusion is the amount of energy released when the substance freezes, and vaporization is the amount of energy released when the substance condenses. These formulas can be found on the back of the periodic table, where there's the one that that refers to a change in temperature, where you're going to use the specific heat capacity. And they even help you to remember this by saying this is the equation to use when there is no phase change occurring. Molar heat can also be referred to as latent heat. So the molar heat of fusion is also referred to as the latent heat of fusion or latent heat of vaporization. And this one you'll remember is the one when a phase change is occurring. And again, a very useful way to remember to use the first equation when there is no phase change is that there is a space in this equation for temperature. During a phase change, hopefully you'll remember from previous lectures, during the phase change there is no change in temperature because kinetic energy is remaining basically constant. So that's why there is no room in this equation for an input of temperature change, because the change in temperature would be zero, but energy is still being applied. Unless you are being asked to calculate the specific heat or molar heat of a substance, these will be given to you. Also on the back of your table, you are given the specific heat capacity and the molar heat or latent heat of fusion and vaporization for water. If you are being asked to do an equation where you are calculating the energy in joules, you want to use 4.18 because that is measured in joules per gram degree Celsius. Likewise, for the heat of fusion, you're going to use the joules per gram degree Celsius, joules per gram. You could also find different values for these if you wanted to. Instead of using grams, you were using moles. You would find a different, for example, the latent heat of vaporization, you would find a different number if you were to be measuring this in moles. So you could find a different number for kilojoules per mole, joules per mole. We're just going to use joules per gram because that's what's given to us on the back of our periodic table for star testing. So let's look at a practice problem. In this problem, we're told that to calculate the total amount of energy needed to boil 15 grams of water at 50 degrees Celsius. A key thing to notice here is we're telling us to boil, which tells us that we're going to have a phase change. And when we look at the temperature, that alerts us that there's going to be a temperature change. This problem is expecting that you already know that water boils at 100 degrees Celsius and melts or freezes at 0 degrees Celsius. So if we are starting with water at 50 degrees Celsius, which is about right here, and they want us to boil the water, that means we need to bring it up to its boiling point. And then if they're asking us to boil, they want us to not only warm the water, but turn it from a liquid to a gas. So this looks like we're going to be using two different equations because this is a two-step process. So again, the first step that we need to calculate then is we need to calculate how much energy is required to warm the water from 50 degrees to 100 degrees C. So again, you would look at your periodic table to remind you of what formulas are available. And we're going to choose the formula that involves specific heat because it allows us to plug in the change of temperature. On the back of the periodic table, we're given the specific heat of liquid water as 4.18 joules per gram degree C. The mass we are given in the problem as 15 grams. And if we're going from water at 50 degrees C to its boiling point at 100 degrees C, then we have a change of 50 degrees. So when we multiply those together, we get roughly 3,000 joules. That is not our final answer, however. We need to look at the second part of the equation, which asks us to then take that water at its boiling point and boil it. Boil assumes they want us to convert it from a liquid to a gas. So notice that when we're converting from a liquid to a gas, the temperature is remaining roughly constant at 100 degrees C. So we're going to choose our equation for this as being the one with the molar heat, because there is no temperature change associated, and this is a phase change. So we're going to choose the molar heat of vaporization, which, given on the back of your periodic table or on any reference table for water, is going to be 2260 joules per gram. Again, we're given the same amount of mass because mass is conserved. 50 grams of ice, when it melts, will still be 50 grams of liquid water. And that 50 grams of water, when it boils to a gas, is still going to be 15 grams. So we're conserving, and we're going to use that same mass again. And that's going to give us roughly 34,000 joules. Again, this is not our final answer. This is just the amount of energy that's required to do the phase change. So the total amount of energy is the 34,000 joules in order to change the phase of the water, and only 3,000 joules in order to increase the kinetic energy of the water to warm it from 50 degrees to 100 degrees. And then here's our final answer. So this is a good practice problem in that it gives us an example of how to do a calculation for a phase change, how to do a calculation for a temperature change, and how to do a multi-stepped problem where you have more than one of those processes occurring.